Good morning, everyone. So my name is Mark. I'm chief scientist at Zamas. It's a startup based in Paris, working on fully homomorphic encryption. So today the talk won't be on fully homomorphic encryption, but just homomorphic encryption. And more precisely, so it will be on additively homomorphic encryption. So additive homomorphic encryption means that if I give you two encryptions, so the encryption of M1, encryption of M2, then anyone can compute the encryption of M1 plus M2. And there is quite a famous system that is due to Pascal Payet back in 1999 that allows to just do that. So that's a public key encryption scheme. So the public key is N, an RSA modulus, which is the product of two large prime, P and Q. And those prime are secrets. And then if you want to encrypt the message M, you just have to compute 1 plus N to the M times some random R to the N mod N square. So that gives you the ciphertext. So I won't detail the decryption, but again, that's quite easy to do. What you have to observe is that now given the encryption of two messages, M1 and M2, if you compute the product of C1, so C1 is the encryption of message M1, C2 is the encryption of message M2, then you end up with the encryption of M1 plus M2. So you see that's quite fairly easy. So anyone given the encryption of M1 and M2 can get the encryption of M1 plus M2. And this is quite useful, so think, for example, to application like electronic voting. So that's an easy way, so assume that you can vote for 0, for example, you agree, you don't agree, 1 you agree, and then you just compute a product of all those votes, and then you end up with the number of people who were voting for 1, so that people who agreed to the election. So that's encryption, and so what we'd like to have is super fast encryption. And for that, so there is an idea that has been introduced for digital signatures, which is the online-offline paradigm. So in that paradigm, so you have two phases. So the first one, called the offline phase, is independent, so in the case of encryption, of the message you'd like to encrypt. And that one can be slow. So you do have time to do the computation. There is also a second phase, so the online phase, that should be super fast. So that one depends on the message. So it means that once you're given the message, you need to encrypt, then you should be super fast to produce the ciphertext. And so the question I'd like to answer in this talk is, how can we get something equivalent to Payet that has a fast online encryption phase? So the goal is really to get the fastest possible online phase for encryption. And of course, so we'd like the scheme to be additively homomorphic. So let's take a look at Payet scheme. So again, so if you want to encrypt a message M, you compute 1 plus N. So capital N is the public key to the power of M times some random R to the N mod N square. And so if we want to transform that in the offline-online paradigm, so there are quite some basic solutions we can think of. So the first one so would be just to encrypt a random message mu. So here, so you can see that C1 is the encryption of some message mu. So just take random message mu, and you compute C1. So that's the online phase. The offline phase. And in the online phase, so when you want to encrypt the message M, you just compute the addition of M and mu mod N. So you see that's online, so it's super fast. You just have to compute a modular addition or two-integer addition. So super fast. There is a drawback. You see that the ciphertext now is longer than the original one. So in this case, so again, so ciphertext C is defined mod N square. So it means that you need 2 log N bits to represent the ciphertext C. In this case, so the ciphertext is given by C1 and C2. And so it means that so C1 is defined mod N square, C2 mod N. so it means that you need 3 log n bits to represent the ciphertext. So you get a very fast online phase, but ciphertext is longer. Something else you can do, so you can pre-compute that random parts r to the n mod n square, and then in the online phase, you just compute this, so m plus n to the m mod c1. So that looks quite complicated, but actually this is not. So you can rewrite the expression for C2, and you see that you can get C2 just computing 1 modular multiplication mod n plus 1 integer multiplication. The second solution has the advantage that the size of the ciphertext, so in this case C2, is just as short as the original PyE encryption scheme. So you see that you just need 2 log n bits. Drawback is that the online phase is no slower than in the previous first solution. So what I'd like to show you is how to get something that is at the same time fast and compact. So how can we get a fast online-offline DCR-based homomorphic encryption scheme? And then, as applications, I'll present you drop-down commitments and chameleon signatures. So let's start. So the basic ingredient I'll be using for the scheme is what I call the ups function. And so that function is quite simple. So given some integer x, you define that the differing fraction. So numerator is just the integer division of x and n, and the denominator is just x. So you see that that value, so the ups function of some integer x, is defined mod n. And so, of course, I need to assume that x is coprime to n. So some property of that function, first, so you can see that that one is defined mod n square. So if you reduce x mod n square, so that won't change the value of the ups function. If you evaluate that function at -1, you get 1. And if you have an integer x that is smaller than n, so +1, in that case, you get 0. And in particular, so if you evaluate that function at 1, you get 0. And a last property, so the ups function of -x is given by the ups function of x plus the inverse of x mod n. So now that we have that function, so we can build a scheme. So public key is just an RSA modulus n, just as for PyE, so which is the product of 2 large prime P and Q, and secrets are those 2 primes, so P and Q. Now to encrypt a message M, so in the online phase, you choose some random R, you compute R to the n mod n square, and then you define a coupon, which is just a pair of integer, so mu and nu. So the first one is just R mod n, and the second one is the f function of R. Then in the online phase, so now you are given message M, what you do, so for, so the ciphertext will be that pair, U and V. U is simply mu, and for V, just add M and nu. So what can you see? So the size of the ciphertext is just a pair of integer mod n, so you just need 2 log n bit to present a ciphertext. And in the online phase, so you just need to do that modular addition. So again, that is super fast, or just 2 integer addition. Now to decrypt, so for that, so you need the secret. So you first compute the Carmichael function of n, which is given by the LCM of p minus 1 and q minus 1. You get lambda. You compute the inverse of lambda mod n. And then to decrypt a ciphertext u and v, you first raise u to the lambda times lambda star mod n square. And then you recover message m by subtracting the ups function of capital U from V, and you get back the original plain text M. So is it secure? So one-wayness is guaranteed by the CCR assumption, so the computational composite resolvability, so the same as the one that defines the security of Payet scheme. And also, so we have semantic security, so under the decisional version of that problem. So exactly the same security as Payet scheme. So the proof are in the paper, so if you want to take a look. So this is homomorphic. So if I give you two ciphertexts, so CT1 is the encryption of a message M1, CT2 is the encryption of a message M2. Then if you want to get the encryption of M1 plus M2, so given those two ciphertexts, so you have to compute that ciphertext, that is the encryption of M1 plus M2. You just multiply U1 and U2, you get the first component of the resulting ciphertext. And for the second one, so you add the corresponding V component of the input ciphertext plus the ups function evaluated at U1 times U2. You can also negate a ciphertext. So you compute the inverse of the first component. And for the second one, so you take the negative of the input one minus the ups function evaluated at U1 times U2 star. So U2 star is the inverse of U2 mod n. So this is additively homomorphic, so it means that you can also compute, so if I give you the encryption of a message M1, you can get the encryption of K times M1. So in that case, so the first component, is obtained by raising the first one to the K mod n, and for the second one, so you compute K times V1 plus the ups function of U1 to the K mod n square. So far, so good? Yeah? So now we have that scheme, and now so we can look at application. And one application so we can think of is what is known as online-offline trapdoor commitment. So if you don't know what is a commitment scheme, so you can think of this as a one-way function applied to some randomized input. So think, for example, I mean, if you want to commit to a message M, what you can do, you can compute the hash value of some message M plus some randomness R. Okay? So that's the committing phase, and then later when you'd like to open that commitment, you just, to some message M, you just reveal the randomness that was used to compute the commitment. Okay? So that's a commitment scheme. So anyone can commit to any message, and you can only open to the committed value. I mean, that's by construction. So there are some variants of that, which is known as trapdoor commitment scheme. In that case, so if you know some trapdoor, then you can open to any message. So if you're given some commitment, you can open that commitment to any chosen message. Okay, so you can always compute the randomness that will open to the chosen value. So in this case, so because we have that online-offline encryption scheme, so we can get an online-offline trapdoor commitment scheme. And what is nice is that you just need one modular addition in the online phase to commit to a message. So this is much better than all known solution. So how does it work? So key generation, so you just choose a random message, MO in this case, you encrypt it, and that will give you the public key. So public key is some RSA modulus n plus the encryption of some random message, MO. And secret key is PQ, so the 2' factor of n plus that random message, MO. Now to commit to a message, so you first, in the online phase, have to compute that exponentiation. So you can see that you are using two random here, S and R. So you get the coupon here, mu and nu. And the online phase, so you just have to compute that modular addition. So again, super fast. So that gives you the commitment U and V. And you can observe that that commitment is the encryption of message M plus S, so some value that was chosen at random, times MO. And to open it, so if I give you some commitment UV, you want to open it to a message M. So you first decrypt that commitment, you get M prime. So of course, you need to know the trapdoor for that, so you need to know the secret key. That gives you the value of S prime. And from that value, so you compute ciphertext C prime, that allows you to recover the value of R prime. So why is that so useful? So again, so you have a way to open a commitment, if you know a trapdoor, to a chosen value M. Okay? So if you now apply that ID to signatures, so we can get what is known as chameleon signatures. So again, so this is a signature, so it means that if I sign a message, you will know that that message is from me, but you won't be able to prove to someone else that I did sign that message. And how does that work? So the idea is, I mean, that's not my ID, but it's a beautiful one. So if you have a trapdoor online-offline commitment scheme, so what you can do, so you can augment the message you'd like to sign, in this case to M at. So you assume that I want to send a message, for some recipient. So I take its public key for the online-offline trapdoor commitment scheme. I can compute the commitment to the message M. I choose some randomness row. And then I will sign that augmented message M at. And no, so because I was using that commitment scheme from the recipient, so the recipient knows the corresponding trapdoor, so it means that the recipient will be able to find another message M prime and O prime that will get exactly the same value for that message M at. Okay? So again, you can sign a message. The recipient will be convinced that this is indeed a valid signature, but he won't be able to transfer that signature to someone else. And so in this case, so because, I mean, that's quite a generic result. In this case, because we have an online-offline trapdoor commitment scheme, so if we choose an online-offline signature scheme, so then we get an online-offline chameleon signature scheme. So just to conclude, so I show you a new way to get online-offline encryption scheme, so that one's quite efficient. So you just need one modular addition or two integer addition in the online phase. And as an application, so I show how to get online-offline trapdoor scheme with chameleon signature as an application. Thank you very much. Other questions? So if you have questions, so please go to the mic so that everyone can. No? Comment, maybe? OK, so I guess it was clear then. Thank you very much. Oh.
Question, do you provide any source code or libraries that we could utilize this algorithm?
No, I don't, but I mean, the primitive you need are very basic. So basically just modular exponentiation. So you can use many libraries for that. Thank you.
Okay, so welcome to my presentation. My name is Malus, and I will present for you my paper, A Practical Compiler for Attribute-Based Encryption, New Decentralized Constructions, and More. So before I start a talk, I always give a bit of a motivation behind the work that I did, so you get like a very high-level idea on what this talk will be about, but also why I actually did this research. So there will be a lot of information on this slide with words that you might not know. Don't worry, I will explain everything later, but it gives you a little bit of a feeling that what this talk is going to be about. So attribute-based encryption, or ABE for short, is a type of public key encryption in which the keys are associated with attributes. And this is in contrast to what you typically see in traditional public key encryption, in which the keys are typically associated with individual users. Actually, attribute-based encryption is a really strong primitive because you can actually allow access control with it on a cryptographic level. And it means that you can store the data on an untrusted platform and still able to enforce access control to it. So what you often see in practice is that they're really interested to use this in, for instance, cloud settings or IoT settings where you typically have a server where you store data on that you do not necessarily trust. However, a problem with ABE is that it's actually fairly difficult to prove security of it. And to simplify this effort, the pairing codings framework was first introduced in 2014. And this really simplifies not only proving security, but also the designing of secure schemes. So if you can more easily prove security of a scheme, you can also more easily design new schemes, because then you don't have to go through the entire hassle of actually doing a security proof. However, the pairing codings framework has some shortcomings, so there are actually quite some practical features that it cannot support that we do really like to see in practice. So you can think of multiple authorities. So typically you have a central authority in attribute-based encryption, but you might not want to trust one single entity to do that, and then you can use multiple authorities to do this. Other examples are hashes and type conversion, and these also help making a scheme more practical in a sort of sense. And in this work, we present a new compiler that does allow for such features. So to give you a high-level idea of what this talk is about, so you're not surprised that I will be presenting things to you, I will first give a small introduction to ABE, then I will give you a small introduction to pairing codings, then I will discuss our new compiler, and to show that our new compiler can actually do things that are sort of desired. We also give new constructions in the paper, but I will only shortly talk about what we actually did, and then I will conclude this talk. So, what is attribute-based encryption? So like what you typically see in public key encryption, we have two users, Alice and Bob. And Alice and Bob may want to communicate. And in this setting, we have that too. So we also have an Alice and a Bob. But we also have something like an untrusted platform that we want to use to store data, such as the cloud. And we have a key generation authority who generates the master secret key and the master public key. And this master public key can be accessed by everyone, and it can be used for encryption. But this master secret key is used to generate secret keys for users. So for instance, Bob in his setting has secret keys for his attributes doctor, Mayo Clinic, and neurology. Then he can request that key, and he can store it on his computer. And now on the other hand, we have Alice, and she might want to encrypt something, so she first downloads the master public key. And then she thinks of, okay, who do I want to share my data with? Then she can specify this in a policy. So suppose that she wants to share it with doctors or nurses at the Mayo Clinic in the neurology department. Then she can specify this in a Boolean formula and then encrypt using the master public key the message that she wants to share with those people. And now she can put it in the cloud, and this ciphertext can be accessed by everyone, but only people who satisfy the policy can actually decrypt it. So in this example, Bob can decrypt the ciphertext because he is a doctor at the Mayo Clinic in the neurology department. And importantly, people who are not do not satisfy the policy, such as Charlie in this example, who's a nurse at the radiology department, cannot, because he does not satisfy this policy. So I'm presenting here the ciphertext policy variant of attribute-based encryption, but you can also enforce policies on the keys and sets of attributes on the ciphertext, but it's not really natural to look at that type of crypto. So for the sake of this presentation, just keep having this in mind. Actually, in this setting, we have a single key generation authority here. So this is like a really trusted entity, and it will issue keys for all of the attributes in the system. But what if we have like a larger system consisting of an insurance company and a hospital, and these might not necessarily trust one another. Okay, so the slides are not advancing. Oh, it's doing something, yeah, thanks. So we're in so everything has to go wrong at a cybersecurity conference, right? It's like, so we're in a setting, and now we have a hospital and an insurance company, and quite naturally, we can sort of feel that these might not be entities that necessarily trust each other, or maybe trust one single authority that they both trust. So we can use multiple authority ABE for that, or multi-authority ABE. And then we can appoint key generation authorities for like every sort of domain that we are covering. So here we have a hospital key generation authority, we have an insurance company key generation authority, and they generate keys for like attributes that make sense within their domains. So for instance, we have Bob again, who's still a doctor at the Mayo Clinic in the neurology department, but Charlie may, for instance, also work at the insurance company, and he's also a patient at the hospital or something like that. And it's really cool because then you can sort of very fine-grained access control across all of these different domains, while these key generation authorities do not need to trust one another to do this securely. So this is actually a really desirable type of attribute-based encryption, and it cannot be covered with the pairing codings framework yet. So now what you need to know about ABE, so like I just mentioned already at the start of this talk, is that proving security of ABE is difficult. And actually, like the more practical features that you add to the scheme, it actually gets worse. So if you have single authority ABE, it's already quite difficult to prove security, but then if you're going to look at multi-authority ABE, it's getting worse. And actually verifying security proofs is also quite difficult already. So this is like a recipe for disaster. So we've also seen that quite a lot of schemes are broken. 2 years ago, also at CTRSA, we also had a paper that we broke like a bunch of schemes. So I really advertise the pairing codings framework for this reason, because it really not only simplifies proving security, but also verifying security. More concretely, pairing codings were introduced by Atrapadung and Wee in 2014. And to give you a sort of idea on what it is, so this is quite abstract, but they're like an abstraction of many pairing-based schemes by just considering what's happening in the exponent. So it didn't tell you anything about the mechanics behind attribute-based encryption, but if you have sort of a high-level idea, so like a lot of cryptographic schemes are doing discrete log things, and now you would just like considering what's happening in the exponent. And actually, by just like reducing the problem to something that's easier to analyze, actually proving security will also become simpler. So to give you like a more concrete idea on what this looks like, so if we have a scheme here on the left-hand side that is like a specification with all kinds of parameter sets and stuff, then you can sort of make like a much shorter notation for the same scheme. So you're just like looking, so these are just polynomials over some variables. And then the idea would be to just prove security of that. Now then you can actually ask, okay, so if we prove security of that pairing coding thing, so that's what's called the pairing coding, then does that mean that this scheme on the left-hand side is secure? And to answer that question, we actually consider the notion of a compiler, and actually it takes sort of this pairing coding as input. You prove security of it, and then you instantiate it as a pairing-based scheme. So the idea is also that you like generically, so you take a pairing coding as input, and then you instantiate it in a certain way with your compiler in an actually full-fledged scheme. And then you prove security generically, given the security of this pairing coding, and you prove security of the pairing-based scheme in that regard. And it allows us to really just analyze the security of the pairing coding and not of the full-fledged scheme, which is much simpler in general. Now, I've just mentioned like proving security of a pairing coding. What does that mean? Actually, there are quite a lot of different security properties for pairing codings. And these also have different compilers, so they're like subtle differences. But what you kind of need to know about pairing coding is that most security properties of it are information theoretical, so like master key hiding. So you look just at the statistical distributions of these encodings that I just put on the other slide, and then you have to show that like alpha in this encoding is like hidden. So it's like very technical talk, but basically it's information theoretic, so that's also a really strong security notion, and it's actually quite difficult to prove as well. So I'm highlighting in this talk more the symbolic property, which is, in my opinion, the most powerful security notion for pairing codings, because it's basically applicable to any scheme that is not broken. And it's also really, really simple to verify. I'm saying simple to verify, which is, like, of course, relative because it's still quite difficult. But what you can think of is like verifying a security proof is just basically doing simple linear algebra. So just like multiplying a vector with a matrix, and then you need to evaluate something. So it's not super difficult. And it's actually really powerful. But currently, these existing compilers, also that use the symbolic property, do not support many practical features yet. And some of these are really usable for practice, so like decentralized multi-authorities. So like we just said, we might not have one single authority that we trust in these different domains, so we might want to have multiple authorities. But we also have hashes, like we want to support hashes to support any string as attribute. We might also want to do type conversion, so that this is like a very abstract word, but basically what you need to take away from this is that you want to do this to really make your schemes really efficient. And these are things that we cannot support with current compilers yet. So if you want to achieve any of these properties, which is very likely if you want to do that in practice, you actually do need to resort to these more difficult proof techniques again. And then you get like problems, like maybe there is like a mistake in the proof and your scheme is broken. So I think a compiler that does support these properties is really desirable. So to that end, I present our new compiler. And our new compiler sort of aims at supporting such practical properties. And to do this, we actually generalize a bunch of things. So we're generalizing the definition of pairing coding such that we can also capture multiple authorities. These actually have a really different structure than the single authority variants that we see. To that end, we also need to generalize the associated symbolic property definition. And to do that, we also sort of use techniques that are used in existing constructions, so multi-authority constructions, to prove security. But this latter point also means that we use a slightly weaker notion of security to instantiate schemes, which is sort of a bit of a drawback. But it still provides like a nice step forward, and also we might actually think that this type of security is strong enough for practice. So to give you a little bit of an intuition behind the generalization, so again, I don't really like to put a lot of math in my talks, but so here there's like a lot that I will not introduce, but basically the keys are group elements. So you can just envision this as h to the power k1, k2, k3. So these just group elements. And here on the other side, we have ciphertexts that are also group elements. And you see here one element that is a paired element. So a pairing is like a function that you compute onto group elements. And the ciphertext here only contains one of them. And this is bad news for multi-authority ABE because multi-authority ABE schemes do not have this form. So kind of the idea behind our compiler is that we can actually handle more of such paired elements, and now we can actually support multiple authorities. So this gives you a really like vague idea on how this works, but if you're like, oh, this looks interesting, go read the paper or come to me, and I'm really happy to explain everything. Yes, so that's basically the compiler. And then you can ask, okay, you have given a compiler, it's like, nice, what can we do with it? So to sort of illustrate that it's actually a useful compiler, I also gave like a bunch of new schemes. Actually, most of them are also decentralized schemes, should not, like multiple authority schemes, should not be super surprising because I also focused quite a lot on it. And to sort of like do something new with it, we created the first decentralized scheme supporting not operations, like negations in the policy, that is almost completely unbounded. So for those who have like a little bit of background in ABE, so this is like a thing that we couldn't do yet. So in general, supporting not operators is very difficult, and we haven't seen it in a multiple authority setting like this before. So it actually can do something like useful and maybe in the future as well. So I would also recommend using this compiler, build new constructions in it, maybe improve the compiler. Yeah, so in conclusion, these slides are not advancing like I want. It gives you like a moment to sink in. So ABE is like a very useful type of cryptography. And what we sort of discussed, so if we want to prove security, especially of these practical constructions that have these nice properties that we want for practice, it's actually quite difficult. So we need to prove security. It's difficult. It's a hassle. So to that end, we have like this bunch of compilers that can do this much simpler. And to sort of support these practical properties, we generalized this compiler to support that. And now it's actually possible to support these practical features much more easily than was previously possible. And like we've seen, we've also given some new schemes that they can actually do this to show you that this is the case. So I hope with that I have convinced all of you that this is a really cool project. And with that, I would like to thank you for your attention. And I'm really happy to take any questions that you may have.
Thanks for that enjoyable talk. So your ABE schemes use bilinear pairings. Can you be more specific about the hardness assumption that you require of the group?
Yes, I can. So thank you for your question. So we're using like a new type of Q-type assumption. So I don't know, like we have some ideally something like the decisional bilinear Diffie-Hellman assumption. That I created sort of a Q-type assumption, so that's like an assumption that grows in the parameter Q, so you have multiple of these bilinear, like Diffie-Hellman-like inputs, and it grows in this Q. So instead of having like G to the power A, G to the power B, G to the power C, you have like Q of these, and then, yeah. And it depends, so if you have a scheme that has a really good security proof, you will actually have decisional bilinear Diffie-Hellman assumption. But if you have like a less effective proof, then you will have more security loss in the assumption. Does that answer your question? Yeah, thanks.
We do have 8 minutes for questions, so if you do have questions for either speaker, feel free to step up to the stand mic, or if you'd prefer to remain seated, I can bring you the handheld.
So, yeah, can I have a question? So I'm a symmetric guy, so I'm not know much about ABE, but what is the input to your compiler? So I mean that you need to somehow interpret what are written in the paper from the specification, and you need some transformation so that the compiler takes the understand what is required. So yeah, that's my question.
Yes, so it takes as input the pair encodings themselves. And also the groups, so like pairing-friendly groups that you're instantiating it. But it's actually really doing it in the most simple way. So you can specify in which of the two groups, G or like the two source groups of the pairing. So you have like pairing is defined over 3 source groups, G1, G2, and GT. And you can specify, so that's also an input that you take, specify in which of these groups you want to instantiate it. And then it's instantiate just like G to the power, the encoding variable that you have.
And this kind of thing must be done manually, yeah, basically, you're right?
Yeah, so it's not automatic. Yeah, so
Yeah,
it's like
sure.
like a mathematical compiler. So it's not. But we're actually working on actually implementing this as well, so that you can give the pair encoding to a program, and it will actually compile it for you, and give runnable code. But I'm not supposed to give too much information about it, so I'm a little too excited here.
Thank you very much.
Thank you.
Any other questions?
Any questions about ABE that you were afraid to ask but never did?
Well, let's have a round of applause for both of our speakers.